Another way to find the solution for this exercise is to really try to calculate d theta dy. So in order to do that, we have to express theta as a function of y. And of course we know that sine theta equals y over r, right? So this is our general relationship. Now, in order to find this relationship, theta as a function of y, we could do something like this. Theta equals sine minus 1. In fact, it's not minus 1, it's inverse. Don't confuse it with this. Sometimes people make a mistake and they think that this is the same like this. And it is like so wrong. This minus 1 here means an inverse function. So theta equals inverse sine y over r. And then we know that from this inverse function here, we can calculate d theta over, but now remember here the domain is y over r, it's not y. So if we were to take the derivatives of this function, then we would have something like this: d theta over d y over r. And by the way, in this example, I think I made a mistake that I denoted it with delta y. Now it's confusing. I'm just going to say that delta y equals y. Alright? So no delta y anymore. I mean just y. So we can take the derivative of this function like this: delta theta over y over r. And then we can use the chain rule. We could find some kind of expression that would give us dy over r, and then we would have dy here. And this is from the chain rule again, right? D theta with respect to some kind of variable, and then that variable with respect to another variable, and then I could cancel out these two things and I would have d theta dy. But in order to do that, I need to find some kind of relationship where this ratio y over r, I need to find out how this ratio changes with respect to y. There is a better way to do it, because what I can do is that I can simply say sine theta equals y over r. Now, what I can do, I can say that this function, sine theta, is k, right? So now k equals sine theta. In order to prove whether this is true or this is true, we need to know something about d theta dy, right? And we already know dy dx. We know that in our example, dy dx was 1. Now, we have to have an idea for d theta dy. So we should have some kind of function like where we have theta equals blah 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 blah, right? So theta as a function of y. However, our relationship that we have is sine theta equals y over r. It's not theta equals y over r, it's sine theta equals y over r. So we can't just say d theta dy equals something. We have to do something about the sign here. And what we do, we're going to use a chain rule, alright? And a chain rule means that, okay, if I have, let's say y1 equals 2 x1. And then I have x1 equals 3x2. And I want to know how y1 changes with respect to x2. In order to do that, the chain rule allows me to do it like this. dy with respect to dx1 times, and now I'm gonna find out how x1 changes with respect to x2. So dx1 with respect to dx2. If I find dy1 with respect to dx1, well, it would be 2. This would be 2. Because if you take this derivative, you would just get the constant. And here, dx1 over dx2 would be 3. So this would be 3, which means dy1 over dx2 equals 6. So we can apply the same thing here. I can say that sine theta is k. And if I want d theta dy, and I know that k equals sine theta, I can write it down like this. dk over d theta. And then I will multiply d theta over dy. However, I am not gonna cancel d thetas now, because I don't need that. I need to know this. Why would I cancel d thetas? Because then I would be left with dk over dy. But I don't want that. I want d theta dy. So I'm gonna leave it alone. And I'm gonna focus on this. What is this? Well, later on we will see, when we learn some of the rules of the derivatives, that if you take a derivative of a sine, you will get a cosine. So, in other words, this would equal dk d theta would be cosine theta. And then I would multiply it with d theta dy. And that would equal 1 over r. Why? Well, because sine theta equaled 1 over r times y, right? So this is like a constant, right? We treat it as a constant. And if we apply this derivative here, d sine theta over dy, which would be this, then we also have to apply it here, d 1 over r times y dy. So if I apply derivative on one side of the equal sign, I have to apply it on the other side of the equal sign. And therefore, I have this equation, cosine theta times d theta dy, that's this. And we got it from this logic that we said that sine theta is k, and then dk over d theta equals d theta over dy, but we didn't cancel out d thetas. So instead we said that dk d theta is cosine theta, and d theta dy is what we are trying to find. And then we also need to take the derivative of the other side of the equation. If we take the derivative of this side of the equation, we also have to take the derivative of this side of the equation, and it's going to be 1 over r. And now, very simply, we can say that d theta over dy equals 1 over r times cosine theta. And there you go. We have found our d theta dy. Now, in our example, theta, the beginning was 0, right? For both beams, 0 radians. And cosine 0 is 1, right? Remember from the cosine function, when theta equals 0, then you had 1, which means this becomes 1, which means d theta over dy is 1 over r. And now, when we know that d theta over dy is 1 over r, so we know that this is 1 over r. We know that in case of the first beam, the r is smaller, right? This is smaller, therefore the ratio is bigger. And in the second case, r is bigger. In the second case, it's 4 meters. So in the first case, it's 1/2. In the second case, it's 1/4. But 1/4 is smaller than 1/2. And therefore, you know that when you have a smaller beam, your d theta dy would be bigger. And the bigger number times 1 would be a bigger d theta over dx. And now you can see that indeed d theta 1 over dx is bigger than d theta 2 over dx. And you have also learned the chain rule, which I was planning to teach you later, but then thanks to this example, you already know it now. But we're going to revise it later as well. So now we have had a lot of videos to build up the intuition for the derivatives, and I think that this is the most important part, because there are many ways how you can learn how to take derivatives of a function automatically. However, if you don't know what you're doing, if you just know how to take the derivatives but you don't know what they are or how you can apply them to real life situations, then it's not useful. And that's why I put so much effort into intuition. And now that you hopefully have strong intuition for the derivatives, in the next section we're gonna start covering some rules. We can always take a derivative using this limit definition as delta t approaches 0. However, it's very tedious. And in the next lecture, we're going to see what some mathematicians came up with to simplify our lives. There are certain rules that we can use in order to take derivatives of any function very fast. Thank you for attending this lecture, and see you soon.